speaker will be Yoonseok Choi from Yonsei University. He's going to talk about Tesla test time reference-free through-plane super resolution for multi-contrast brain MRI.
Okay, thank you for the introduction. Let me begin with the motivation behind this study. Most brain MR scans, especially T2 and FLAIR, are acquired anisotropic resolution, which means the in-plane resolution is fine, but the through-plane one is much coarse. So this is done to save scan time and preserve SNR. But it comes at a cost, which is a degraded structural fidelity, which limits accurate diagnosis and analysis. And here's where the gap appears. Most existing SR models focus on in-plane resolution enhancement, but modern MRI scanners already handle that using built-in deep learning method, which is deep resolve. The real clinical bottleneck is through-plane resolution. And surprisingly, this is still underexplored in many deep learning approaches. So there's a mismatch between what SR models optimize for and what clinicians actually need. So another issue is how multi-contrast MRI is used. T1, T2, and PD emphasize different tissues but share the same anatomy. However, most existing multi-contrast SR models just fuse them in a black box way, ignoring their structural similarity. So this not only wastes the valuable information, but also makes the model less transparent and hard to trust. And in clinical practice, if a model isn't trusted, it won't be adopted, no matter how accurate it looks. So with these challenges in mind, our goal becomes clear. We want to improve through-plane resolution, which is the real bottleneck in clinical MRI. And we also aim to leverage structural consistency across multi-contrast MR scans in a meaningful way. And most importantly, we want results that are trustworthy enough for clinical use. So now let me introduce our model, Tesla. It's a two-stage pipeline. So the first stage is progressive reconstruction. The low-risk target is progressively refined to minimize structural discrepancies with the high-risk target. And also, by doing this, we can actually reduce the domain gap between the shared anatomical contents of the low-risk target and the high-risk reference. This alignment builds a much stronger foundation for the next stage, where we can finally leverage multi-contrast information in a more effective way. So stage 2 is called structural enhancement. So once the target is structurally aligned with the reference, we focus on explicitly refining the anatomical details in a modality-aware and clinically consistent way. Here's the idea. After stage 1, we get a soft SR target. So of course it's improved, but still missing fine details. So we align the smooth target contents with the high-quality reference feature in the latent space by using patchwise contrastive learning. That way, the model pulls together structurally similar patches and pushes apart unrelated ones. Next, we enhance the edges using a conditional patch scan guided by the edge map of the high-res reference. This forces the model to recover sharper edges and more faithful structure. Finally, we enforce data consistency. The SR output is averaged along the slice axis and compared with a downsampled raw image. This ensures that the results are not just visually plausible, but also physically consistent with the scan protocol. Now moving on to our data sets. We tested Tesla on 5 different MRI data sets covering both reconstruction and segmentation tasks. They spanned a range of slice thickness from mild to severe anisotropy, allowing us to test both image quality and downstream clinical utility. Here are qualitative results on the HCP dataset. As you can see here, Tesla consistently recovers final anatomical details than existing methods. For example, look at this subtle hypo-intensity near the fissure. Only Tesla is able to reconstruct them even with the 8 times downsampling. These are pseudo-vessel reconstruction results from our in-house datasets. Tesla not only reconstructs the vessel itself, but also preserves the surrounding anatomy. Now let's move to the downstream evaluation using the BRETS 21 dataset. Here we ask, how well does each model's SR flare support tumor segmentation? This is a good test of whether the SR image truly preserved structural information or not. So first, when we use T1 weighted images as the reference, performance dropped, especially for the edema and enhancing tumor class. And the reason is simple, because T1 lacks the tumor-specific contrast. So given that drop with T1, how about T1CE? Let's take a look at it. Now, when we switch the reference to T1CE, the segmentation improves significantly because T1CE provides the tumor-related information that's really needed for accurate reconstruction. But there's a trade-off because T1 weighted scans are much more commonly available in the clinical practice, while T1CE requires contrast injection. So the key insight here is this. Reference choice is not just technical. It actually reflects a clinical balance between accessibility on one hand and lesion-specific information on the other. These are the quantitative results of all the experiments. Across all data sets, Tesla has achieved the highest value. We also ran an ablation study to find the best high-res reference. This is critical in multi-contrast SR because the reference choice directly impacts the output. So from the IXI datasets, the fourth row using high-res T1 as a reference produced the most coherent and consistent results. And we also observed that high-res T1 provides the most dynamic structural features, making it the most effective reference modality. To summarize, Tesla improves technical transparency by extracting only the shared structure from the high-res reference instead of black box fusion. It also supports reference-free inference at deployment. And it's the first reference-free through-plane SR model validated on both healthy and pathological datasets. So overall, Tesla shows a strong potential to bridge the gap between SR technology and clinical needs. This is all for my presentation. And for more discussion, please find me in my poster. Thank you.
Okay.